Sure, it's bright and loud. And scary. But if you watch lightning from space, you can learn a lot about storms. Like how soon the really bad winds are coming. Or hail. Or tornadoes. You see, people are building this new satellite. It'll be like a superhero with magic vision, watching out for us all the time from high above the Earth. It'll take hundreds of pictures of the cloud tops every second to find lightning flashes, even ones that don't hit the ground. And if a whole bunch of lightning starts all at once, well, then the weather people will know that bad stuff is just about to happen. And they'll be able to give us more time to get ready and go to a safe place. Pretty cool, huh? Sure, it's bright and loud, but it doesn't have to be scary.
When the next generation of NOAA geostationary satellites, GOES-R, launches in 2016, it will deliver highly advanced data and will continue an important legacy of Earth observations. The primary sensor on the GOES-R series is the Advanced Baseline Imager, or the ABI. This instrument will image Earth's weather, climate, and environment and will improve every product from the current GOES imager. With as many as 16 spectral bands, the ABI instrument will deliver a greater number of products with 5 times faster coverage rate and 4 times better spatial resolution than the current GOES imagers. Faster means improving real-time forecasting capabilities. With ABI on board, GOES-R will deliver rapid scan images every single minute, allowing forecasters to get a much quicker update on developing atmospheric events. ABI will be able to produce a full scan of the Earth in 5 minutes, which is another significant improvement over the current 30-minute scan. Better spatial resolution means that ABI will deliver spectacular 3-dimensional visuals, along with enhanced detection of the early stages of severe weather events. ABI's data will help meteorologists zoom in and track an area of developing storms in much greater detail. Knowing how rapidly storm clouds are forming will mean earlier warnings for people on the ground. ABI will track and monitor cloud formation, atmospheric motion, convection, land surface temperature, ocean dynamics, flow of water, fire, smoke, volcanic ash plume, aerosols and air quality, as well as vegetation health. Better data quality and faster scan speed will contribute to fewer weather-related flight delays and incidents with volcanic ash plumes, as well as earlier preparation for tropical storms and hurricanes. By delivering a better and larger suite of weather, climate, and environmental products, ABI is poised to become a true success story, benefiting the public by enhancing the nation's weather prediction capabilities.
From its unique location at the L1 Lagrangian point, almost 1 million miles away from Earth, the Discover satellite is an important tool for monitoring space weather. Variations in the solar wind can cause geomagnetic storming, which seriously impacts many important systems here on Earth. And the EPIC Earth-directed imager provides us with a view of the Earth not possible from other satellites. The GOES geostationary satellites are located in an orbit 22,500 miles above the Earth. GOES East and GOES West continuously monitor weather systems all across the Western Hemisphere. These satellites use customizable image scanning strategies which allow us to monitor cloud formation and movement in real time. However, additional important information can be derived from other parameters sensed by the satellites. All of this data is used on a regular basis to formulate weather forecasts and warnings issued by the National Weather Service. Scanning the Earth from only 500 miles above the surface, polar orbiting satellites offer spectacular views of many different features, including hurricanes, wildfires and smoke plumes, solid sea ice and free-floating icebergs, and even the brilliant glow of city lights at night. Additional derived parameters are also important for use in atmospheric computer models, which provide key guidance to National Weather Service forecasters. You can go online and learn more about NOAA weather satellites and see satellite data in real time by going to the NESDIS website at www.nesdis.noaa.gov. Thank you for watching.
Schultz at the University of Alabama in Huntsville, and I would like to talk to you today about lightning jump algorithm for the GOES-R geostationary lightning mapper using proxy data set. This is based off work started with Schultz et al. 2009 and 2011 that made or developed a lightning jump algorithm using lightning mapping array data, three-dimensional lightning data, which is a ground-based network. They applied this algorithm to help to look at lightning jump, increase in lightning activity, and use a statistical threshold to consider or establish a lightning jump. This lightning jump has then helped to predict or forecast severe weather, or we've been correlated to see how well it forecasts severe weather. Schultz et al. 2011, the algorithm works very well, and as we're getting the GLM lightning mapper coming on with GOES-R, we want to see how that worked with a data set that would be similar to what we would see from the space-based satellite, space-based data. So we took that algorithm and applied it using this proxy data set that was developed using lightning imager sensor data and the ground LMA data to create a database of what splashes look like from space and from the ground. That database is then used to create this proxy data using statistical relationships where we used 2002 through 2011. What we did was we applied, we looked at two different verification methods as that can change the results. When we say results, I'm talking about our property detection and our false alarm rate. When we applied the algorithm, we had different tunable parameters that we're looking at to do sensitivity tests. We looked at the sigma threshold, which is a statistical threshold that the algorithm used. We looked at flash rate threshold, the time the algorithm spun up, and then for verification, looking at the report distance from the storm, as we know there can be error with that, and then our forecast period, and then with our database, the domain range that we use from the center of our network, and the spatial scale when tracking with the WITSI algorithm. Here we have some of the output from that we're tracking. Here we have our 5-minute flash counts, which on an average 5-minute on a 1-minute basis, and then our reflectivity. And then for this, we tracked most use reflectivity base to track. We combine the lightning data and the radar data using this VIL flash rate density product. We tracked on that, and we can see our cells as you see here. And so we take these cell tracks, or these cluster tracks, and those were our clusters that we would then apply our algorithm to. We applied the algorithm, and we did some sensitivity tests, and so far what we have found is that the flash rate threshold and our sigma, or that statistical level that the lightning data must reach to say a jump has occurred, those seem to have the most influence to influence our probability detection and a false alarm rate to help use this in an operational framework. So we hope to go forward with this and tune the algorithm